You had a question about molecular hydrogen, correct?
Yeah.
So we did, this is the old one, this is the new one, we did this, or we did a lot of it. Remember that?
Yes.
Do you remember when we did this? Does this look familiar? And yours might be more filled in than this one.
Yes.
Perfect. And you had a question about hydrogen, correct? Okay, so we used hydrogen in stuff, right? So it's like when we did water, we put some hydrogen on. When we did the methane, we put some hydrogen on. But we didn't actually do straight molecular hydrogen in an atomic diagram, correct? Correct? Is that right? That's not right? You know what I'm going to ask, don't you?
Who's brave?
Who's brave? Who's brave? You're brave? H2, molecular hydrogen. Come on in, come on in.
This one here, right? H2?
Correct, correct. Awesome. Can you walk us through?
If I get my notes making.
Perfect. This is the surprise twist. He didn't know he was walking us through. It's okay. When I do the walk us through, it's like it has two, each it has one shell because it's in the whatever row. It has this many valence electrons because it's in whatever column. That's sort of how I sort of do the walk.
Yeah. I basically just, in order to write the molecules themselves, because we did other ones beforehand, like H2O.
Right.
Make the individual molecule already, and I knew that bonding these two electrons here would work because even if they shared the maximum that they can have in that first shell is 2, and obviously this doesn't make them exceed that.
Right, cool. And molecular hydrogen, each one is a hydrogen, which is element number 1. So there's how many protons? 1. Awesome. Good job, sir. Good job. Perfect. What do you think of that? Does that do it for you? Perfect. 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 Here's a question for you. I don't need to take a picture. That's right. Ooh, wait a second. Take a picture of it. We did not do atomic sodium, the one on the bottom left. And that's going to be one for us today. So where's sodium? Where's sodium? Where's sodium? Third row.
Did we change that to oxygen? Oh, yeah.
Did we?
Yeah.
Oh, cool. Well, great. Good job. Let's change it back to sodium. Let's flip it over and let's do sodium. Flip it over. Let's just flip the piece of paper and just like an NA. Whoops.
On the right top.
Okay, cool. How can I spin this to make me not look like an idiot?
NaCl.
See, that's one I'm going to hand out for today, though. Yeah, so I got to come up with a different one.
Na. What is Na?
Sodium.
Magnesium.
We can do magnesium. That's an excellent idea. Who's brave?
Not yet.
Who said magnesium? Nobody's going to cop to that, right? Mg, what is that, 12? Okay. So change the sodium that we already changed to something else in magnesium on the back of your piece of paper. Who wants to give it a crack? Magnesium. You're among friends. Go for it. Fancy chalk. I'm top shelf. So we're doing one atom of magnesium. We're just doing one, so we only need one. We only need one magnesium.
And switching it up on me.
I know. What element is it? How many? What number? 12. Cool. In G, bless you.
Yeah.
I'm an ordained minister of the Universal Life Church. If I can bless people and conduct weddings. So if we stopped right here, hang on a second, let me get do we have a pause button? We don't need to put a pause button. It's like, boom, pause. If we stopped right here, what would that be? If we stopped right here, like, if this was a 10, put a 0 right here. Yeah, if we were stopped right here, what would this be?
NE.
Which is
Neon?
neon. Cool. Would that be reactive? Would you be able to react this with anything if this was like this?
No.
No. Why not?
Because it already has P.
It already has 8. Its valence shell is full.
Yeah.
There it is. Boom. Okay. Back to mechanism. Are we there?
Yes.
We're there. Can this react with stuff? Yeah, it's super reactive because the valence shell is not full, super empty. Good job. Love it. So what do all of these things here have in common? What do all of these elements over here have in common? Noble gases, what do they have in common? Yeah, they all have a full valence shell. So that's why all of these are super not reactive. Because like the valence shell is full. There's no bond sharing that can happen, right? Because like it can't covalent with anything because its shell is already full. So they're going to do exactly what we all do sometimes, which is just sort of sit there alone. Sit there alone. Decrepitude. Is this clear?
Yes.
This good? Make sense? Is it all coming back?
Yes.
Perfect. Can I erase or do we want to take a picture? You know, I like this. I like this. You know, because this is the math, right? Of like, you have this many protons, so when you add shell 1, shell 2, shell 3, you know, add those up, that number is going to come up to that number. So you know you have, you know, it's going to be 288 if they were full. So it's like, this is a good notation. I dig it, right? It's clear. It's super clear. Good? Good? Perfect. Are there any other questions about any of these on the handout from Tuesday? Any other questions? Questions, thoughts? Like 15 pounds of things. Do you want to give that a minute and let it settle? Cool. Welcome back, folks. Do you want to keep those or do you want to do something with them?
What is do something and take?
I don't know. Take it with, give it to me. It's like, just hang on to them. Just need the sun right. The sun right. My mother, from an early age of me, would acknowledge that I don't always think about the consequences of what I say. Because I'm like, what do you mean? I don't actually know myself. And hang on to one of these. Distribute these amongst yourselves. Can we do the same thing we did last time? Where it's just like, give it to the corners and make it rain. I think we're still in chapter 2, which is still we're going to go through bonding, like chemical bonds, bond types, and things like that. And next week we'll probably get into like macromolecules, fats, carbs. So next week we'll take the start of chapter 3. We might finish up chapter 2 today, depending on how we feel about acids and bases. We'll see. Have you ever been in one of those classes where the instructor was married to the syllabus and like come hell or high water, they're going to do on the syllabus what they said they were going to do? right? And it's like, nobody asks any questions, right? We're gonna do what we're gonna get through. The objective is to get through it in those cases. Rest must have been not like that. Any leftovers? Any extras? There should be pretty colorful things on the back.
Oh,
Yeah, perfect. They look very similar to the other one, except for the pretty colors on the back. We'll get to the pretty colors on the back here in just a minute. But you can see that all of the boxes on the front of this are not atoms, they are molecules, right? There's some, on 5 of these 6 boxes, there are covalent bonds that are bonding the thing. In one of them, there is an ionic bond. You with me? Let me see that. Perfect. And we'll get into what that is here in a hot second. Who feels like they can do oxygen and water? Oxygen and water. Who feels like they can do that?
On the border in general?
Like in general. Are we comfortable, right, with that kind of stuff?
Yes.
Great. You have 3 minutes, which I'm not going to time. Go ahead and do the first 2, the oxygen and the water. And the key objective here is making sure that everybody in the room is present and able to do it, and you're going to look out for each other and help each other if somebody needs it. All right? This is an everybody's in it together exercise as well. So if you need a little boost, feel free to say, hey, can somebody help me out? End my lecture for today. How we doing? We there? Just about? I'm not trying to rush anybody.
Almost.
Just about. Hey, what's going on?
A covalent is when the electrons are shared.
Correct. Correct.
Oh, I haven't seen somebody use this since elementary school.
I got this image from the internet. We good?
Yes.
Perfect. We did CH4 in class, I believe, quickly on Tuesday. Is that correct? I think we did it super quick.
It's like a diagram.
Yeah, it was like I did a carbon, hydrogen, circled all the things. That's when we were talking about how many things can bond to other stuff, which is neat because if you think about the 4 most abundant elements in living biological systems, they are carbon, hydrogen, oxygen, and what do you think the other one is? What do you think the other one is?
Iron.
That's not a bad guess. Not a bad guess. Nitrogen. Nitrogen. And by the end of next week, I think you'll know why. The cool thing about these 4 is this. If we just kind of make this general statement, just kind of based on what we've been doing so far with how the periodic table is structured and playing around with drawing atoms and now drawing molecules, how many covalent bonds can you make with hydrogen? 1. How many can you make with oxygen? So what oxygen is
6.
8 protons, 1, 2. Once you bond here, once you bond there, the shell is full, right? So 2. How about nitrogen? How many covalent bonds can you make with nitrogen? 7 protons.
3.
So you can do 1 here. 1 here, like 1 here, and then you're at 8. 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen would be
3.
3. Carbon. It helped that it did those in order. So back when I was a wee lad, back in the 1970s, 1980s, we had toys in the house, and they were different in some ways from the toys that we get today. They were mostly like old-timey stuff, and like, here is a rubber ball. You know, because like that's sort of all we had back in the day. But there was this awesome toy called, this set of toys called Tinker Toys. You've heard of Tinker Toys?
Yeah.
Well, you say that, but you know,
No,
sometimes
no,
you're like,
I-
I have no idea what, there's people out here that have no idea what Tinker Toys are. So what are Tinker Toys? Who started them? What do they do?
Do you like logs that are wooden that you?
Yeah, they're like long sticks
With like the little circles.
and little circle things.
Yeah, you plug them in and then you go.
And you plug in the sticks into the circle things and you can build all kinds of things. What made Tinker Toys fun is that there were things that you could put on the ends of the sticks that had 1 hole in them. And there were things you could hang in 2 holes. And there were a few things where you could put like 3 holes on it, make like 120-degree angles. There was another one you could put 4 holes into, right? And the diversity of structures you can build with a set of Tinker Toys is not necessarily about the different sticks that you have. The diversity of different things you can build with Tinker Toys is how many of the little connectors you can have, how many holes do they have, and at what angle. You with me? So when we think about biological systems, much like you're a biological system, what are the 4 most common elements that we see that make up like overwhelmingly, like over 95% of every atom in your body? It's these 4. These are your Tinker Toy set. You have something that can bond to one thing, which a lot of things use as a placeholder. It's like I have an extra valence, I have an extra space in my valence shell, and I need to bond it with something so I don't keep reacting with other stuff. I'll just put a hydrogen on it and fill it up, right? It's almost like a molecular, put a cork in it with a hydrogen and we can be done bonding that way, you know? Oxygen, right? So if you want to connect two things together, you can use an oxygen. If you want to connect threes, you can have a nitrogen. If you want to connect fours and do the whole kind of grid lattice work stuff, you can use carbon, right? So in a lot of ways, the molecular diversity that you see in biological systems is because these four things operating together give you a pretty serious set of the connectors you can use. And of course, the sticks, you know, the equivalent, biological equivalent of the sticks are the covalent bonds, right? So no wonder this is your molecular tinker toy set where the covalent bonds are the sticks. And you can make all kinds of stuff out of this. Good? Clear? Perfect. Perfect. Awesome. Let's go to NH3. Anybody know what this is called? There's a word for this. You know it.
Oh,
It's ammonia. Ammonia. Nitrogen has, so it's like when I'm looking about this, it's like I'm looking at the thing that I think is the central hub of all of this. It's like, because I mean, I was going to look at this like, okay, so how many protons does nitrogen have? Why am I starting with nitrogen and not hydrogen?
It's the biggest one.
Because like, yeah, it's the big one. It's in the middle. It's like, it's sort of the thing that's the thing. And the hydrogens are just like, just fill in whatever's left over space with hydrogen sort of as we go. 7 protons. Are you brave? Not yet? We'll get you there. How many electrons in the innermost shell? Just so you know, the answer is always 2. Let's talk about hydrogen. If we stopped right here and this was a 2 and a 7, that would be helium. And it would be done reacting,
yeah.
correct? Because the shell's full. How many electrons do I have left? 5. How many covalent bonds can I make from the previous conversation? 3. One, 2, where's my other? 3. So in this case, it's like you have an element, like an atom of nitrogen, and the hydrogens are just like, I'm going to attach on to each of these free electrons out here until it's full, and then we're going to be done. So 1, 2, 3, 4, 5, 6, 7, 8. Super stable and abundant in the solar system, not particularly reactive in a covalent way. You can do some weird ionic stuff with it for reasons which we'll get to at about 1040. You know, but all things considered, ammonia in H3. What do you think? Makes sense? Chemistry is easy. Everyone goes, oh, chemistry. Questions about ammonia?
How does it add up to 8?
You have 1, 2, 3, 4, 5, 6. You have this extra lone pair, unbonded electrons hanging out over here in the shell. Yeah. So it's like you don't get to just bond stuff to every electron in the shell. You have to stop at 8, which means sometimes you get these sort of lone wolf pairs that sort of hang out over here. And those pairs that are hanging out over here in the outermost shell that are unbonded, that has consequences, which we'll get to a little bit later on. Okay, go for it.
Okay, how do you get the 7 proton? I don't even see.
It's the N right here.
Oh, I saw the N center, but I was like, where's? Oh.
So here's the 7 protons. So it's 1, 2, 3, 4, 5, 6, 7. Yeah, these are outer shell electrons that are not covalently bonded.
So that's what I'm doing. The number. Okay.
Yeah. So the number of the red number, the 7 is the number of protons. And we're sort of sticking for now with our rule from Tuesday, which is like, we're just going to have the same, we're doing electrical neutrality. So we're just going to have the same number of electrons as we had protons. But that's, you don't always have to do that, but just to get us started here, we'll do that. And we'll do ions here in a second. Great. Questions about ammonia? Oh. Okay. Two kinds of covalent bonds. Polar and non-polar. Look for some props. Ooh. The things you can find in a college classroom desk drawer, like a bag of leftover Smarties. Who wants candy? You can have some on the way out. Science first. Treats later.
It's not old candy.
Oh, I can guarantee it's old candy. Yeah, but yeah, Smarties. It's like I don't think anything. It's pretty. Talk about inert chemistry, right? There's really not too much in here. Do you know how the solar system works?
Gravity.
Pretty much. If you had to have a one-word answer, and we're talking about like the large-scale structure of the universe, gravity is usually the answer. All right. So you have this big thing in the middle called the. If you ever really get the feeling like you're really actively participating in class, there are some spectacularly easy questions that I ask a lot, and you go, "Ooh, sun," you know. It's like, yes, full-on participation level. And it's big and it's bright. It shines out death and destruction and everything around it. And we're far enough away that it doesn't kill us too quickly, but everything gets us in the end. And there's a lot of mass in there. There's a lot of stuff. Do you know what a star is?
The sun.
We have now engaged in full-on circular logic, right? With a conversation. What is a black hole waiting to happen? I have not heard that answer before, and I love it. That's right up there with like there's a casket with your name on it, just waiting for you to kid, right? A star is a black hole waiting to happen, right? That's a glass half empty situation. How do they work? Do you know? How do they work?
They be stars.
I mean, you look out there, there's like something's going on up there, right? I mean, so how do stars work?
They emit light when they explode.
The emit light, yes. They use the word explode. That's funny, right? Chemical reactions that release energy are not really happening in stars. So it's not like kaboom. It's not like a stick of dynamite's going off. It's something else. It's as if we took all of you in this room right now. I'll be the observer here. And we're going to smash you into the middle of the room so that you occupy the space like something the size of, I don't know, super, super tiny. We're going to be smashing your atoms so closely together that the actual nuclei themselves of the atoms that make you up are going to start to fuse together. They're going to fuse together. Yeah. And the cool thing about it is gross. It's gross when you first start the squeezing. By the time you're at the nuclear fusion phase, you're pretty mushed up by then, so it won't be as gross. But when you think about, okay, so how's this going to work then? Here's hydrogen. If you think about how much energy there is, like total E equals mc squared energy there is in an atom of hydrogen, and if we smash two of those together really, really hard, we would think that the total amount of energy in those two atoms is the amount of energy in one times two, double it, right? And as long as they're separate, that's what happens. If you look at the total amount of energy of one atom of helium, which is, you put the noble gases on here, all the way over there with two nuclei, you would think that would be the total Einsteinian E equals mc squared energy of two of those. So you take two hydrogens and you smash them together so hard the nuclei fuse, and now you don't have two nuclei with one proton, you have one nuclei with two protons. So the energy would then be of helium is twice as much, correct? But it's not. It's a little bit less. It's a little bit less. So where did that extra energy go? It left in the form of light and heat, right? So it's like, that's what you're seeing. You're seeing the differential in fused versus unfused nuclei in a star as things are getting smashed together, getting expelled outward, right? And so what the actual star itself is, who has ever been in a bad relationship? That can include any nature of any, it can include a bad relationship with your parents, it can include a bad relationship with your siblings, with your pets, with yourself. It can include a bad relationship with anything, right? Relationships are a funny thing. There's some sort of force holding things together. You could call it attraction, you could call it obligation, you could call it, resulting personal need, whatever it want to be. There's something that's holding stuff together. Yet simultaneously, there's something repellent about them, right? Because it's like everybody gets tired of everybody eventually in the end, right? Nothing lasts. Everyone will always, eventually everyone will leave, right? You know how this goes. I'm just saying, it's like, I call it Paul time, when it's like, I get kind of punchy. It's like, I think I need some Paul time, or I'm going to go be by myself in a cushion in Massachusetts for a week. So there's this force pushing inward on relationships, that is this attraction, call it gravity, call it whatever you would want. There's also a force pushing outward on them, right? And in the case of stars, that force pulling in is gravity, right? Things have mass, they attract each other, get gravitational attraction. Sound good? And as they fuse, since there's so much gravity, you get this big energy release, which is then a force pushing outward. So you get this tension. You get gravity pushing in, at the same time you get energy pushing out. And that maintains a state of equilibrium that changes through time as the star goes through its stellar cycle, right? So when you're looking at the sun outside, not directly, for about 4.5 billion years, give or take, this star has been doing this thing where gravity's pulling in, but the energy is pushing out. And so sometimes, the energy coming out of it waxes and wanes, and you get sunspots and stellar cycles, Milankovitch cycles, and with the eccentricity of the orbit of the Earth around it, that, relates to how much energy is coming into the Earth from the sun. And, we hear about red giants, these stars late in life, they get really, really big as that energy relationship starts to change. You have this whole stellar evolution of this thing, right? All the while representing this tension between gravity pulling in and energy pushing out, right? So that's sort of so I think of stars as like relationships. If we think about what's really fueling this thing, like I was talking about, right? It's these atoms being squeezed by gravity so hard, with the nuclei actually getting so close together that the nuclei actually fuse into a united one, which is the way to get things to move from this side of the periodic table to this direction. So if we're taking 3 or 4 different atoms and smashing them together, they're going to move to the right on the periodic table, correct?
Yes.
Yes. Cool. And if you keep doing that, not only are they going to move to the right, but they're also going to start moving down on the periodic table. This is changing one element into another by changing the number of protons in the nucleus. We're not fooling with electrons here. We're literally changing the nuclei through brute force gravity. Okay? So when I think of stars, it's like they're engines to move right on the engines to move to the bottom right of the periodic table. That's what's happening in stuff. Go ahead.
So as they continue to mash together, it increases electronegativity.
We'll get to that in a second, right? There's a fun thing going on, right? Because it's like, as long as you're moving this way, electronegativity is increasing, but once you start going down, it starts decreasing it again. We'll get to this trend in a second.
Because you said it decreases in energy, right? The more they smash, it decreases in energy.
It doesn't double, right? So you would think it would double as you went up to the next
But instead
one
it
up,
decreases.
but it's like, helium has more nuclear energy than two hydrogens do, but it's not double, it's a little bit less. Right, so that little fractional difference
Oh, so
is the energy kicking up. You still get more, but it's not double. So energy is
And
lost in that
the
reaction.
electronegativity, the energy?
It's not, but it's similar to it. You're gonna love this one. Okay. So you have all this mass going on here, and then you have these planets. You know, Mercury closest in, yes? Who knows their planets? Mercury,
Venus,
in order, Venus,
Earth,
Earth,
Mars,
Mars,
Jupiter, Saturn,
Jupiter, Saturn,
Neptune, Uranus, sort of Pluto.
yeah, Uranus, Neptune,
No.
equivocally Pluto.
Yeah.
Right, it depends on what you do with Pluto. Technically, it's kicked to the curb. Going out in that direction, right? So there's Mercury, Venus, Earth, ... All that kind of cool stuff, right? And here's Elon Musk. Here's a SpaceX rocket, right? And he wants to send this thing into orbit, correct? Who's ever seen a rocket launch? Anyone? They're really cool. You ever go down to the Space Coast and see something go up? Right? It's brighter than you would think. Like you watch them on TV, it's like, yeah, Elon's smart. Wow, look at that rocket go. When you do them in person, it's like, holy shit. That is a spectacular amount of energy coming out of that thing. Absolutely spectacular. What direction does Elon fire his rockets? Initially, up. If you've ever watched a rocket launch, like and paid attention to it, it doesn't go up for long. What does it start to do? It starts to turn pretty quickly. I mean, it goes up, it's like up, but ooh, it's starting to turn, it's curving, right? When you fire a rocket, you don't just go up, because the rocket fired straight up, what will happen to it? It'll just come straight back down, right? So you have to do this turn. You know what the turn is called? It actually has a name. I get so excited about this stuff, it's great. It's called a gravity turn. It does a gravity turn. They go up, but after 80, 100 kilometers, it is literally going parallel to the surface of the Earth as fast as it can. Because it doesn't want to go straight up and come back down. It wants to go in orbit. To stay in orbit, you don't have to go up as hard and fast as you can. You have to go lateral as hard and fast as you can. I could, or someone could, if they wanted to, they could make like a baseball go into orbit. And you wouldn't have to throw it up. You could just throw it that way about 30,000 miles an hour. And it will be going so fast, gravity will be pulling it down to the Earth. But it's moving so fast that it is moving around the curve. You with me? So that's what Elon is trying to do. Make rockets go so fast that gravity will always win in the end. It's the gravity is pulling on the rocket, but the rocket is going so fast that it's always falling past the Earth. That's what orbit is, right? So you have to put tons. Here's the rocket rocketing along. Tons of energy into this thing. Tons of energy into it, right? You have to get this thing up around 24,000 miles an hour, right? Fast, super fast. Fast enough that it can be moving in this direction, always falling that way, but always missing. Okay. Gravity will win in the end. It always does. So that energy represents kinetic energy, energy of motion. You with me? Perfect. I'm going to take a picture of this, but it's pretty much indecipherable. Wait till we talk about cells. I can find this slide real quick. So you have a nucleus of an atom. Let's pick one. Let's pick one. For some reason, I'm having a hard time picking one.
Bromine. Is that too high?
Bromine.
Sorry. I just like
Which one's bromine? 35? Yeah, let's go something little. I love bromine myself. It's like I'll be up here all day drawing electrons. I don't know. We like our friend. Well, let's go with hydrogen. Let's start simple. What's the charge on this nucleus? What's in here?
Oh, positive.
Yeah, so it's positive, right? This is a positively charged thing. And the electron outside of it is negative. What do you know about opposite charges? They attract each other. So what prevents this electron here from crashing into this nucleus? Why doesn't it just fall in?
neutral.
It has something, right? It has, what does the rocket have?
And
It
energy.
has energy, right? There's an energy associated with this electron, a potential energy, right? Like when I remember their gnats buzzing around your head situation, you know, it's like, well, the gnats have gravity and your head has gravity. Why don't the gnats just like crash into your head? In space, they would if everything was just sitting there over periods of time, right? But they have this energy of wing flapping and all that kind of stuff that keeps them from falling into your face, which they sometimes do anyway. So how much potential energy does it have? That much. Does this make sense?
Is that just a squiggle?
It's a squiggle. It's from here to here, they have that much potential energy. Or were you talking about this? Because that looks like a squiggle
No,
as
no, no,
well.
you got it, you got it, you got it.
Like, it's hard to read too, just FYI.
What did this say?
Potential energy. Potential energy. So whereas when we're talking about the solar system, we're talking about gravity as the force that provides that attraction. In this case, we're talking about electromagnetism, right? The attraction between opposite charges. That good? Make sense? A little bit cool. What then, my brilliant, beloved students, whom I adore, what can you tell me about, if we move up to lithium, element 3, we have another electron here that has its potential energy, and then we have another electron up here on another shell. What is the difference between this electron and these two?
It has more potential.
Yes. Yes. It has to, because it's farther away from the attractor. Right? What about an electron all the way out here? If this was like some big thing, this one would have
A lot more.
even more, a lot more. It would have a lot more. To hold it away from the attractor, it must have more energy. More fuel got it into its orbit. Good? Perfect. They talked about this like in your previous chemistry classes, right? This is all that. Good, good, good. We're gonna use this. So you're seeing this, because I do realize you might have for the last 20 minutes been wondering why the hell is he talking about stars and solar systems and Elon Musk and rockets? I get that a lot, it's fine, right? What does this have to do with bonds, like covalent bonds? It turns out a lot. It has a lot to do with it. Rather than changing the distance of the electron from the proton, let's change the number of protons. So here you have hydrogen, potential energy, great, right? No problem at all. So that's here. That's right. Let's go up to the next level and look at beryllium. That is element 4. 1, 2, 4. So these electrons have that much potential energy. These electrons have that much. Let's go up to element number 5, which is element number 5. What's the B stand for?
Boron.
Boron. Right, boron. Boron. So we have to add another electron, correct?
Yeah.
We'll do that. Awesome. This electron is carrying the same amount of energy as these, right? In terms of like distance from the nucleus.
Yeah.
But now there's more positive charge in the nucleus.
So it's stronger than.
It's getting pulled on harder. The shell starts getting pulled in. If we go up to carbon, 6 protons, they're not falling into the inner shell. The whole shell is getting pulled in because now there's even a stronger. We're at 6 plus at this point. If we go up to nitrogen, 7 protons, add another one. There's now, it's like you're adding more mass to the sun and the planets are getting pulled closer to it because now there's more gravity. You're adding more positive charge to the nucleus. So the electrons are getting pulled in closer, like the whole shell is getting pulled in closer. So it's like you have the space station is orbiting at 120 kilometers up, give or take. And then you add 20% to the mass of the Earth. It's going to get pulled closer in. It might still stay in orbit, but it's going to start getting pulled closer in. The strength, the force that a nucleus pulls in on the electrons is called electronegativity. So it's like lithium is super, super low. We're looking at just like the outer shell here, lithium, the electronegativity is super low. 1 point, it's like the lowest one out there. Okay? There's only 3 protons of the nucleus to pull. And that outermost electron is in that second shell out. There's not a lot of force there. This electron might just actually like fling off into space. There's so little pull on it. When we get to beryllium, electronegativity is starting to go from 1 to 1.5. It's going up, right? We added another proton to the nucleus. And so it's pulling harder on the valence electrons. Boron, it's up to 2. Carbon, it's up to 2.5. Nitrogen's up to 3, right? So when you think of nitrogen, you're still in the same outer shell as lithium, but now you have 7 protons pulling on that outer shell, not just 3. So you're getting even more. By the time you get to fluorine, the most electronegative thing there is 9 protons pulling on those electrons, right? But you're still pulling on that outer shell, which is really, really close in. You're still only out to Venus at this point. Make sense?
Why is it 4 there?
Why is it what?
I lost myself in the last part when you were explaining like the 3.5, the 4.
Why does it go up?
Yeah.
The outermost electrons are still in the second shell,
Okay.
correct? But you're adding more attractive force in the nucleus.
Okay.
So just that shell compression.
Yeah, so the shell's getting pulled in from the negative. So it's like the solar system equivalent is the sun is getting more and more and more massive as you go. Mercury, Venus, and Earth are getting pulled closer and closer in, just because there's more attractive force. Question?
Yeah, I just want to make sure I understand. So
It's a tricky one, right?
So
It's not a linear. You have to understand about 2 things at once. Go ahead. Sorry.
So the more protons that are in the nucleus of the atom, the smaller the space is going to be of the shells themselves.
Yeah. So the outermost shell here is going to be closer in than the outermost shell here.
Does it only affect the outermost shell or all of the shells?
All of them, the outermost. The outermost one is the one where we track electronegativity by them, for reasons which we'll get into when you talk about polar and non-polar bonds. So it's all of them. We spend our time talking about the consequential one, which is the valence one, though. So, but all of them, yeah.
The valence is the only one that increases the electronegativity?
We only think about it with the outer one. It's all of them, but it's only the outer one that reacts.
Okay.
So the outer one is the consequential, sort of consequential one.
Okay, but regardless of the proton by number increasing and the shell compressing, the nucleus is like its role in that. Is it just because the protons increase, the nucleus will increase?
Yeah, well, the nucleus is getting bigger and bigger, but the
not the nucleus, sorry, the neutrons.
the neutrons are, just kind of doing that thing.
Oh, okay. I thought the neutrons like is what causes the pull.
No. Yeah,
Just
just
the
the
protons.
protons, just the
Okay.
protons, yeah. So there's like a couple of things going on here. It's like, so the nucleus is getting bigger, you're adding protons, it's getting more positive. What are the consequences to the valence shell because of that and all the shells, right?
Get small.
They get pulled in the more you go. And so you get to fluorine, which is 4. If you add one more proton, you get to neon, great. Add another one after that, you get to sodium, element 11, and your electronegativity crashes down to 0.9. Why? Because you have to add another, which is
Awesome.
way farther out. You have to add a third shell, and so you just increase the distance. Right, so you have even more protons here in the nucleus, what you did there, but you had another shell, and because we're tracking the valence ones, it's way far out. It's way far out. And then, because that third shell keeps we kept packing more electrons, we packing more protons, so it starts to go up 1.5, 1.8. It's never going to be as high as here, just because it's far out. You get a chlorine, big thing, 3. You had 2 more protons. Now you drop to 0.8. 0.8, right? So it's like, it's even more, but now you have to add a 4th shell, which is, we're out at Mars at this point, right? So it's like, there's this balance between how much attractive force do you have in the nucleus and how far away is the valence shell. And when you consider those two things together, you end up with these values referred to as electronegativity, right? Electronegativity. Tell me what you don't know. Question, yeah, actually,
I know that the numbers it's like saying like 4 is obviously the most, but is there like the number itself, is there a specific reason why it is that number? Like what that
so, like, what's the math behind the number 4?
Yeah, like even 0.8. Like I mean, I don't know, sorry.
What the number is.
What the number is, yeah. This is a fun, electronegativity values have no units. It's a non-dimensional number. Experimentally derived. The numbers 1 or greater can participate in bond sharing in a covalent attractive way. What lithium, sodium, potassium, rubidium, cesium have in common, not hydrogen, but these actually are more like, when the lower the number is, like these super below 1 numbers, they will usually more often than not take that outermost single valence electron and they will dump it. They'll get rid of it. They're more stable by getting rid of this and is carrying a positive charge, calling themselves an ion at that point, a cation, than they will something else. So more often than not, this outermost valence electron, it's held so loosely, it will usually just like fly out of the solar system and something else over here will steal it. But if they attract each other, we call them salt, like sodium chloride and stuff like that, which is not electron sharing, it's electron stripping. Right? We'll get to this on next week, right?
The attractive force is basically the proton.
Yeah, this is the magnet on your refrigerator. Right? You take a magnet and it's attracting.
Right.
It's that. I mean, that is the electromagnetic electrical force.
So
It's the same force that's attracting the electrons to the protons. But the electrons don't crash in. They're held up here by this energy, but there's still a force pulling them inward.
Right. So when you say increase the attractive force, that's like increasing the amount of protons.
Correct.
Okay.
Correct. So you're not at 1 plus, no, you're 2 plus.
Right.
Now you're at 3 plus, 4 plus, 11 plus, 12 plus, right? 7 plus, 8 plus, 9 plus. So fluorine is the highest because it's the thing that has the most protons in the nucleus, with the closest in valence shell. This will react with all kinds of stuff, highly, super, profoundly reactive. Question?
I don't know if you already answered this, but what is the bottom row in that 1A, 2A, 3A, 4B?
I don't know whose convention that is. I don't use it.
Okay.
Yeah. Is it similar up there? They also kind of go with this, 3D, 4D, those are the orbit, 12D, 13, 14, 15. Yeah, they do weird stuff with the metals.
Okay.
That means something to someone. I don't know.
I don't know if we need to know it or not.
You don't.
Okay.
You don't, right? Question?
How come hydrogen is higher than the rest of the ones on the left? Is it because it's like the gases instead of the rest, or?
Why is it 2.1? So why does it drop? And there are these little kind of interesting kind of waves that you can see throughout the whole thing, right? It's not just straight linear thing. It's like a trend. It's like a trend that sort of happens. That might partially be the effect of neutrons. I don't know. Let me get an answer. Let me get an answer for you. I don't know. Yeah, because it's close. 2.1 to 2. There is a drop. Maybe some of the electronegativity gets washed out because you are actually spreading the positive charge amongst more electrons, but not quite.
Is it because it's kind of reactive? Like it reacts with a lot of different, I don't know.
I don't feel comfortable enough to actually say yes or no to that. Let me get an answer for you. So why does it drop before it goes back up? Right? Looking at the periodic table, in general though, there's this trend, least electronegative going upward to most electronegative. And so I just wanted to go through why does that number go up when you head in this direction? I may or may not have successfully done that. Long story short, the higher the electronegativity, the stronger it's pulling on valence electrons. And electrons that are participating in covalent bonds. So if you look at hydrogen, one proton, yes?
Yes.
Yay. Look right? Believe it or not, that's a 1. There's a covalent bond. You have 2 bonding partners. These hydrogens have the same electronegativity value. Correct? Both of these nuclei are being held right in the middle of this bond, directly in the center, right down the middle. They're sharing 50-50.
So is there no pull?
There is no pole. So that is a non-polar covalent bond. Finally, the point.
Wait, can you say that all again?
We've arrived at the plot, right?
Can you say that all again?
However, if we have our water molecule, the protons, use 1 proton, innermost, and then electronegativity, hydrogen is 2.1, oxygen 3.5. Those electrons are really getting pulled in to the oxygen side of this in that covalent bond. So it's not equal sharing on the covalent bond. More often than not, the shared electrons are being pulled into the oxygen side because it's more electronegative.
Oh, so because the protons in the oxygen is stronger than the 2 hydrogens, that's why there's more pull?
Yeah,
Making it
there's more
polar.
pull. Yeah, so it's not just the oxygen's own valence electrons, it's also the valence electrons that it's sharing get pulled closer in to the oxygen side, to the more electronegative element.
So whenever it's equal and there's no pull, it's non-polar.
Correct.
If it's not even.
If the bonding partners differ in their electronegativity, there is a pole.
When it's not even.
When the electronegativity's values are different, you get polarity. And what do we mean by polarity? How many, so if we draw a line representing, okay, here's the water molecule, here's top half, bottom half. See it? My line, yes? How does it work in high school? 1, 2, 3, look at me.
It has to rhyme.
It's like 1, 2, look at you, or something like that, right? Yeah. My class last year was doing this. 1, 2, 3, look at me. All right. So if we draw a line that splits the water molecule in the top half, bottom half, here's a proton, yes?
Yes.
How many electrons are on the top half? How many electrons are up here on the top half? None. They got pulled down here. So we do this weird sign. Looks like that. Partial positivity. Every once in a while, the electrons might like vibrate up in this direction to go there. Most of the time, they're down here. On the bottom half, how many protons do we have on the bottom half? Oxygen side is 8. How many electrons are down here most of the time? 8,
6.
9,
10.
10, because it's pulling the hydrogen ones. So this side is going to be partially negative. So these are polar covalent. This is a nonpolar. So if you're ever wondering, oh, is this bond polar or nonpolar? What are the differences? Is there a difference in electronegativity across the covalent bond? So what happens is if we have lipids, fats, things like that, you with me? Oil, Crisco, whatever it might be. Long carbon chains. This whole string. Non-polar because,
They share the same.
yeah, it's electronegativity down the line, right? Here's our water molecule. Positive, negative, positive. Here's another water molecule. Negative, positive, positive. Right, that you mix the oils and the fats in the waters, what happens? They separate. For things to dissolve in water, they need to have partial or full charges hanging off of them. Molecules that have these long carbon chains, these non-polar ones, do not dissolve in water because there are no charges up here to attract the water molecules themselves. So they separate out by density.
What is that little design you put next to the positive and then the negatives?
That
Yeah, what is that?
Conventional Greek symbol that they use for like partial positive. What is it, rho? Partial positive, partial negative. It's not a full charge. If it was a full charge, we would be talking about ions, cations, and anions. Salt, we'll get to that next week, right? So it's like most of the time the electrons are here, but sometimes they're up here, like 10% of the time. So it's like it's this partiality. It's a partial charge, not a full charge. It's a 0.7, 0.8 and change. Question.
So if the bonding partners like electronegativity differs, then it's polar?
The more different they are, the more polar it is.
The more, okay.
Yeah. So we make this out like, well, there's polar and non-polar, and there's everything in between, right? Water is pretty much the extreme case of the difference between the 2.1 and the 3.5, right? Because they're on opposite extremes of the periodic table. That's a superpolar molecule, superpolar, right? So what kind of stuff dissolves in water? Things that these, salt, sodium with a full charge, chlorine with a full charge, other polar molecules. We call water the universal solvent. Most things dissolve in water, correct? Which tells you most molecules in the universe are polar. Non-polarity molecules are kind of rare. It's only like these oils and fats and things like that,
Oh, is that why water and oil don't mix?
That is why water and oil don't mix, and it's also why we use lipids for cell membranes to keep the inside in and the outside out. More about that in a couple of weeks. Question?
What's soap made out of? Like, is
Oh yeah, that's interesting, isn't it? Soap is fascinating because it's like you can do this thing where you take your hand and you jam it in a tub of Crisco. Correct? Who's done that? Really?
Yeah, for cooking.
Yes, I love that. Right? It's like, I was kidding. One handful of Crisco. So you just,
For like.
or you get like oil on your hands or something like that, and you put it under the faucet and turn the faucet on, and the water hits it, and what happens?
Oh,
The water just like
Yeah.
kind of flings off of it, doesn't actually go anywhere. So what do? You
So,
take soap or a detergent, and you put it on your hands. What soap does, I'm going to keep this picture up here because it works. It's this molecule. Here's our soap molecule. Half of the soap molecule has a negative charge, and the other half of the soap molecule is nonpolar.
Oh, so it gets.
So the nonpolar side attaches to the fat, the polar side can interact with the water. So it does, so the fat comes off of you and goes down the drain, right? These molecules that are partially, they're charged on one side but not charged on the other, we refer to as being amphipathic. Amphipathic.
What's that mean?
Half of the molecule is polar and half of it's nonpolar. So those molecules have the potential to act as detergents. So you can give. However, in biological systems, the prime suspect of a molecule that is polar on one side and nonpolar on the other is called a phospholipid, and you make cell membranes out of them to separate the inside of the cell from the outside of the cell, which we'll talk about in a couple of weeks.
I'm sorry, I missed it. Could you say what the definition for amphipathic?
Amphipathic,
Yeah.
it's a molecule where half of it is polar and half is nonpolar.
Thank you.
And so it has the ability to like strip nonpolar fats and lipids off of your skin and send them down the drain. Go for it.
on like the polar side, if the molecule has more protons, whatever has the most protons will always be the one that has the negative potential. You know what I'm saying? Like,
Is that true? Let me look at the periodic table. There might be a couple of weird exceptions up here, right? When you start to get into
sorry, like what do you? What,
no, I'm trying to come up with like, is there a counterexample? I think I know what you're asking, right?
Because like what makes one side positive, what makes one side negative?
The positive side is going to be the less electronegative. The negative
Okay.
side is going to be the most electronegative.
Okay.
So these things over here are usually going to be the negative side, and these are going to be the electropositive. So we say these are like super electronegative. Conversely, we could refer to these over here as being super electropositive. These are going to be electron acceptors. They're going to be pulling electrons closer to itself. These things over here are going to be pushing electrons away from themselves. These things over here are going to be electron donors. These are going to be electron acceptors. These are going to be called oxidizers. These things are going to be called reducers. Oh, we have the rest of the semester to go and don't write any of this down, right? You may have heard some of these things. But what do you do in your car? You turn your car on and the engine turns on and you're combusting something called gasoline, correct? You're taking something like this that has a bunch of carbon-carbon bonds and you're combining it with this thing that is super electronegative. The oxygen is going to attack that bond, pull the electrons closer to itself from where they are. The electrons are going to be reducing their potential energy because they're being pulled closer to an oxidizer, closer to a very electronegative molecule. Energy is going to come out, and your engine is going to run. Right? So that's how engines work. That's how you make bombs. That's how you do all kinds of stuff. You take non-polar covalent bonds, you mix them with an oxidizer, and you light a match to get over the potential energy hump. And boom. Right? You're changing the potential energy of electrons by changing bond polarity. Don't do that. Two things. Don't make bombs and say that you learned how to do it in Paul's biology class. Stay away from methamphetamines. Right, those are my two rules for this weekend. No meth, don't make bombs.
What about the weekend after?
Well, YOLO, right? We'll see what happens. We'll save that for next week. There's a spectacularly huge amount of information that got downloaded today. Okay, so let's not minimize that, right? The best thing to do is nothing, right? So it's like, go home, go to bed, let it sit. When you come in on Monday morning, you'll be like, oh yeah, I guess. We'll revisit this again, after it sits for the weekend, but you'll learn when you sleep and when you take a shower and when you're out for a walk and exercising. That's when integration actually sort of happens. So there's no expectation that you actually learned anything in class. You get exposure in class. Your brain, give your brain time and space and patience to do its thing and work itself out. And you're not expected to be an expert on this today. Okay? Oh, yeah, you can take it and do it. Right?
Do we have lab class today?
We do not today. We will start our first lab next Thursday. It's Wednesday. Next Thursday, we'll do our first lab. So you get the rest of the day to not do methamphetamines and not make explosives. And what a killjoy. Oh my God.
No fun.
I would, but Dr. F told me not to. What's for dinner tonight?
Whatever mom makes.
What was for dinner last night?
Chicken.
Marry me chicken.
Yes, I was going to be methamphetamine, but now methamphetamines and bombs, but now it's going to be chicken. I've never said that before.
No level.
51 years. This is one of those no extra cost courses. So don't let the bookstore try to sell you something unless it's like a Slim Jim or something. But no extra materials for class. Everything that you need, you already have within you.
That's deep.
And on the internet. And on the internet. Or from the copy machine upstairs that gives and receives. Perfect. So yeah, no lab manual. We'll get everything we need to do in lab. What I found is if there's actually a lab manual, the objective of lab is to get through the lab manual. But if you don't have one and you're left to suffer alone on your own in lab, you'll learn a lot more. You'll learn more by doing less without the objective of trying to get through it.
Yay.
Yeah, it's great. That's great. It's perfect.
Oh, are you posting your textbook next week?
But doing what?
Didn't you say on Canvas that you'd be posting your textbook?
I think it's already there, isn't it? Can you get to the OpenStax book?
Oh.
Yeah, it's
Oh, so there is a textbook, but
there's a but it's a free online
if we want to read.
OpenStax if you want to read it, which you may or may not want to do to answer the homework questions, which we're due
Yeah.
Tuesday.
For the homework questions, do we write them down on a piece of paper?
Yes.
Okay.
Yeah. My Bio 102 class said, wait, what? Right? Because you mean I'm not submitting it on Canvas? And I was like, no, you're writing it down on a piece of paper and you're bringing it in.
Ew.
Disgusting.
No, I
It's
appreciate
gross. It is absolutely gross.
That's not very.
You will learn so much more
When you write it on.
with your hands.
That's not very eco-friendly.
Write the question, write the answer.
I don't,
What?
but we have to read, we have to bring the questions, write them down.
I know, that's what I was saying. It's ridiculous. Who does this? I mean, might as well
Or just the
send it by
answer.
Pony Express.
No,
Do you want the question and then the answer?
No, I just need the answers.
Okay.
But yeah, so bring the answers on a piece of paper, write your name on it, and set them down in the most eco-destructive way.
Wow.
Is that all under
A
modules?
scientist.
Yeah. If you click on the assignments link,
Oh,
they'll show up.
assignments.
Yeah, click on the assignments, they'll show up. Yeah, I'm old school. What can I say? I used to do a whole lot of Canvas, turn it on Canvas, turn it on Canvas. And either it was completely illegible or it turns out it is pretty easy to copy and paste. So, write on a piece of paper.
That's the only homework?
Oh, we have a lifetime.
No.
We have an
next class.
absolute. I would invite you to look at the assignments link
Okay.
in Canvas and see what's
Oh,
cooking for
gotcha.
you. See what you're doing this weekend. See what you're doing this weekend. There's a couple things, right? There's a discussion post.
YouTube video.
Turn it in.
Yeah, that's it. It's just a discussion.
Just, yeah, I think so.
Do Thursday. Today, at 11.
You guys are great.
Chapter 2 questions, 1 to 19.
Yeah, can we just skip chapter 1 because who needs it?
But we're not doing
What?
that. We're not doing chapter.
That's what I said.
Who needs it? You know who does chapter 1? Nobody. Nobody. Chapter 1 is like so less. It's like we're just over it. We're over chapter. I mean, there's nothing in chapter 1 that you're not just going to figure out along the way just by doing the rest of them. So it's like I'm gonna tell you what I'm gonna tell you. It's like let's skip that and just get to the unnecessarily complicated descriptions of Elon Musk, how rockets work, and electronegativity and bond polarity. Good? Perfect, right? So let me know if you have any questions about anything. Hit me up on the canvas. Do you want a Discord group or not?
Yeah.
Okay, I'll launch a Discord group and I'll put an invite as well if you guys want to jump in. I am extraordinarily accessible via like Canvas or anything like that. If you have any questions, let me know. I'm even happy to like record answers and kick them back to you. Follow me on Instagram, TikTok, Twitter. I can hang on to it. Today's is this one, correct? Today's is that. That's okay.
Copy.
I hear you.
That's
crazy.
a question, just to make sure like I completely get the basics.
Okay. Correct.
And then up here it increases, down there, the number of cells is greater, so as it decreases.
The outer shell's closer in.
More in?
Yeah,
Okay.
yeah, that's it.
Cool.
That's it.
All right.
And so it's like, this is not so like the numbers here and all this is like, this is the emergent phenomena of that happening,
Okay.
right? So it's like, that's why these numbers are sort of non-dimensional.
Mhm.
And they have no actual like unit to them. Because like, it's sort of an arbitrary measurement of
Okay.
the attractive force of the proton on the outer shell.
Mhm.
You know, so it's not in nanometers, it's not in Gauss, you know, it's just
Yeah.
like this non-dimensional, how hard, you know, so it's like when you balance out the base, so how far away is the outer shell and how many protons are there? You observe this arbitrary 1.6, which since it's a weird thing, is probably reference to
Yeah, I was just about to
lithium,
ask.
a 1 or something,
Okay.
you know, so it's like, there's the number, it's like this, if you're talking about like motion and like physics, there's this number called the Reynolds number, which describes how structures move through fluids. It's a non-dimensional number. When you actually calculate the number, all the units cancel out. And it's like the Reynolds number is 4, and it's like 4 what? It's like it's not 4 anything, it's just 4,
Okay.
but it describes, you know, how long your airplane is going to be in the air before it crashes, you know? And it's like this, the electronegativity is the same way. This is a spectacularly high electronegativity number.
Okay.
Fluorine is going to rip the electrons off of anything else in the periodic table, which is why it's so monstrously toxic, right? One of the most lethal things out there is fluorine. You know, oxygen, super high electronegativity as well. Not quite as toxic as fluorine because you're soaking in it now. But you're also oxidizing yourself to death, right? Oxygen is really, really reactive. And it's like stripping electrons off of everything it can find, especially these lone wolf oxygens referred to as free radicals. So you need a lot of antioxidants so you don't die soon by being oxidized to death, you know, by a hyperreactive ultra electronegative molecule out there. But what oxygen is doing, and this is the story of respiration, what we're going to learn about when we talk about mitochondrial aerobic respiration, you're actually relying on that super high electronegativity value because you are trying to get the energy out of nonpolar covalent bonds.
Yeah.
And in order to get the bonds out of the food you eat, you need something highly electronegativity that can break those covalent bonds and reduce the potential energy of those electrons. So you need something over here. But not that much because it'll kill you. And nitrogen is not quite enough.
Okay.
And plants make a lot of this, so it's cool.
Awesome.
It all sort of is like, just wait for it.
Okay.
Just wait for it. You know, but it all
Makes sense.
comes together in the end, you know? It's like, so if the question is ever, how do we get the energy out of this bond? Grab something highly electronegative, and it'll interfere with that bond, yank the electrons off of it closer to itself, and some energy will come out.
Got it, okay. All right, thank you so much.
If you ever want to put electrons in, grab one of these things.
Oh,
It'll shove the electron into the bond, and you can break it that way. You can break bonds either way. Which is neat.
thank you.
Bye. Questions? Thoughts?
You had a question about homework.
Yeah, so where can I find the 19 questions that we have to answer on the Google line?
Yeah.
Yes.
You just scroll through them, there's like 24 questions, but I think we only answered the 18.
Yeah, because I think I could have done after that, I think. Didn't I? Or like that and 3 of the other ones or something like that. I don't know. I can look myself.
Is there a link to the textbook on the Canvas itself?
I believe there.
Yeah.
There.
Okay.
Do we have to repeat the questions?
No.
We answer,
So just
say
answer.
the number.
Yeah, just like number 6, B or something. Yeah, that's
It doesn't
Thanks.
show up on your phone sometimes, but that should be the link.
Okay, perfect.
Wait, what is that?
So if you're in the
Are you on
if you're in the Canvas,
And then that's the textbook.
you can go to the
And you just keep
Assignments.
scrolling until the
two
answers
on there.
come up. All of this text and
Okay.
keep going to next, and 24 questions. Next one. And you keep going. Then it's just.
bless you.
As we go on.
Okay, I was gonna sneeze. What's going on? You doing okay?
Yeah, I had a question
Sure.
about, like the lab coats and everything like
Okay.
that, because I wasn't sure, like, when to get those, or like,
Don't.
okay.
I give you everything you need for that. Don't let the bookstore sell you something.
Okay, and then,
Oh,
what is the
yeah.
question? Oh, yeah. Is me being gone for this,
Oh.
I'm gonna watch the videos.
Is you being what?
Is me being gone for
Yeah.
those 2
Oh.
days, and like, is that gonna really affect anything? Or, because I'm gonna do the assignments and
Pardon me,
everything,
I'm sorry.
and watch that.
Thank you.
Yeah, bye-bye. Take care.
Sir,
It's hard to anticipate.
Cause like
Right,
cause like for my, like I had like math classes and everything, and I was gone for like 2 days for the classes, and then it came back and it was fine. But I just wanted to know since this is a class, but I think I can stay on top.
Everything's gonna be fine.
Okay, all right.
Everything's gonna be fine.
I hate when I leave like for
Rule number
vacation.
1,
Stay calm,
Stay calm.
be fine.
don't freak out.
Don't freak
Don't freak out. Yeah, everything's not, and you're not freaking out, right?
Yeah.
You're expressing a concern
Mhm.
based in reality, and it's a legitimate one.
It's
right?
just funny when there's a bio class going on, you're on vacation, it's like.
Yeah, it's because your body is on vacation. Your mind is
Yeah.
going to be on that biology class that you're
Yeah.
missing. I hear that.
Yeah.
For sure. I totally hear that. And when is that? That's the September.
Yeah, so September, I'll be gone for the 6th and the 8th of
Okay.
those September classes,
You'll
the
be
first
fine.
week, yeah. All right.
You'll be fine. This is something that the later us can address when it happens.
What was that?
With the later us can come back to this when it gets closer and when it
Yeah,
happens to
yeah.
see what we need to
I
do.
always think about that.
So it's not, so, the question, am I going to be okay with it? It's like, I don't know,
Yeah.
probably. The pragmatic side is that it's like, what can we do to make sure that you're okay? Because that's a question that gives us somewhere to go.
Yeah.
It's like, that's a question we can actually do something about.
Mhm. Yeah, I
Right.
mean. I think
But it's like,
I'm gonna
I
be
post the
fine.
videos, I mean,
Yeah. I think it's stress in the beginning, and then when you actually come back,
Yeah.
and then you're finally like, oh, that wasn't a big deal.
yeah, because, I mean, no, it's like, no, this is a big deal.
Yeah.
No, this is a big deal. You're awesome friends.
Okay.
Boom.
All right.
Have a great day.
You too. Have a great weekend.
For the 19 questions, do we have to read like the chapters or can we just answer them?
Just answer them as best you know them, right? Yeah, if you know them, just answer them.
So the point.
So the assignment is to turn in the answers, it's not to read the chapter.
Oh, okay. So like,
Oh,
even if they're right or wrong,
that's
it's just complete.
Ladies'
Try your
choice.
best.
I use.
Like, I mean, if reading the chapter is the way that you get there, read the chapter. If it's not, it's not. I mean, Khan Academy.
So it's mainly for completion.
It's mainly for learning, because you will learn things by writing those answers down and turning them in. You will learn, you can't escape learning
Yeah.
through that method,
Okay.
right?
Yep.
Yeah,
Try your best, that's it.
try your best and then check your work and then turn it in and we'll go from there.
Okay.
I think it's gonna be awesome.
Thank you, have a good
Love
one.
you, you're awesome.
I just had a question about the water holder. So
Sure.
is it like, are like the hydrogens like being pulled into the oxygen?
The covalently bonded electrons are being pulled in.
Okay, and it's
And the hydrogen probably a little bit.
Okay.
but it's the bond that gets, the electrons in the bond that get pulled in.
Okay. So like when you why do you split it in half just to show?
There, we don't have the equal balance of electrons on the bonds anymore.
Okay.
They really are being pulled more down in this direction
Okay.
than in that direction,
Okay.
you know?
All
And so the degree of that offset of like how strongly you're being pulled in this direction is proportional to the electronegativity value.
right. Okay.
So, and the difference between hydrogen and oxygen is large, 2.1 to 3.5. That's a strong pull down in this direction, which is why water is like so polar,
Right.
it's super polar,
Okay.
super polar.
All right. Thank
Yeah,
you.
sure, awesome. Okay. Have a good weekend, okay?
You too.